All right, let's talk about things that spin. Anything that twists, turns, or just goes around in a circle. Today, we're going to break down the physics of rotational motion, and I promise it's way more intuitive than it sounds. So let's just jump right in with the classic mystery. You've seen this a million times, right? A figure skater is spinning, they pull their arms in, and bam! They suddenly become a total blur. They didn't push off the ice, nobody gave them a shove. So where in the world does that crazy burst of speed come from? Answering that is going to be our main goal today. Now, to crack this puzzle, we are not going to learn a bunch of new complicated rules. Nope. Instead, we're going to see that for pretty much every concept you already know about things moving in a straight line, there's a rotational twin. It's really just about translating what you already get. And that's the great news here. You already have a gut feeling for how forces in motion work. We're just going to take that same exact logic and apply it to things that are spinning. So think of it less like learning new physics from scratch and more like learning a new, specialized language. Okay, so before we can really dig into the forces, we've got to get our vocabulary straight. I mean, how do physicists even talk about things that are spinning? Let's build our own little dictionary, comparing the linear world to the rotational one. The translation is actually surprisingly simple. So in linear motion, we ask how far did it go, and we measure that in, meters or feet. For rotation, we just ask how far did it turn, and we measure that as an angle using units like degrees or, if you want to be a physicist about it, radians. And guess what? This pattern just keeps on going. For how fast, we have velocity, right? Meters per second. Its rotational twin is, and you probably guessed it, angular velocity. That's just a fancy way of saying how quickly the angle is changing. In other words, it's spin speed. And finally, if we want to change that speed, we talk about acceleration. Its twin is angular acceleration, which is just how quickly the spin speed itself is changing. See that? It's a perfect pattern. Distance, velocity, acceleration, they all have a rotational counterpart. Okay, we've got the language down. Now let's talk about what actually causes all these changes in spin. We know a force makes things move in a straight line. So what makes them start to rotate in the first place? Well, the answer is this fantastic concept called torque. Think about opening a really heavy door. If you push right next to the hinges, almost nothing happens, right? It's super hard. But if you push on the handle, way out far from the hinges, it swings open pretty easily. That's torque in action. It's a twisting force that depends on both how hard you push and how far from the center of rotation you are. So here it is, the direct translation, the big connection. Just like a net force makes an object accelerate, a net torque makes an object have an angular acceleration. In other words, torque is what makes things change their spin. It's the perfect rotational twin of force. Simple as that. All right, now for the other side of the coin. We all know some objects are harder to push than others because of their mass, their inertia. So what makes some objects harder to spin than others? The answer is something called moment of inertia, and this is where it gets really, really cool. It's basically an object's rotational laziness, its resistance to being spun up or slowed down. But here's the key difference. Unlike regular inertia, it's not just about how heavy an object is, but how that weight is spread out. This chart just illustrates the point perfectly. Imagine you've got a solid disk and a hollow hoop, and they have the exact same mass. The hoop is way harder to get spinning. Why? Because all its mass is distributed far away from the center. The disk, with its mass spread out more towards the middle, has a lower moment of inertia, so it's much easier to spin. So there's our next twin. Moment of inertia is to rotation what mass is to linear motion. If mass is an object's resistance to being pushed, then moment of inertia is its resistance to being twisted. It really is the object's stubbornness against changing its rotation. Okay, we have all the pieces now. We have spin speed, that's angular velocity. We have rotational stubbornness, that's moment of inertia. Now let's put them together and finally solve the mystery of that figure skater. The solution lies in one of the most fundamental, rock-solid laws of the universe, the conservation of angular momentum. Now, in simple terms, it just says that for a spinning object, if there are no outside twists or torques acting on it, its total amount of spinness has to stay the same. Now let's look at our skater through this lens. When her arms are stretched out wide, her mass is distributed far from her center. As we can see in the table here, this gives her a really high moment of inertia. So to keep her total angular momentum constant, she spins at a relatively low speed. And here is the aha moment. When she pulls her arms in tight, she's yanking all that mass closer to her center, which drastically lowers her moment of inertia. But the law of the universe says her total angular momentum has to be conserved. So the only way for the math to work out is for her spin speed to shoot way, way up to compensate. Low inertia means high spin speed. It honestly feels like magic when you see it happen, but it's just this beautiful, elegant demonstration of a core principle of our universe playing out right there on the ice. She's just masterfully manipulating her own moment of inertia to control her velocity. It's not magic at all. It's just physics. And that kind of leaves us with one last big thought. This very same principle that governs a spinning skater also governs how planets orbit the sun, how entire galaxies form their incredible spiral arms, and even the bizarre behavior of subatomic particles. So the question is, where else in the world around you can you spot these invisible forces of spin at work?